Okay, dear students, okay, let me share about the concepts of the electromagnetic radiation. So here, electromagnetic radiations are a form of the energy, Okay, when we are discussing, before we discuss about the energy, so let us remember the three famous scientists. So who are they? Number one is the Albert Einstein, number two is the Max Planck, and the third one is the Louis de-Broglie. Okay, so they have a different concept, they have a different theory. So according to the Albert Einstein, his theory's name is the theory of relativity. Theory of relativity. In this theory, what it found that the energy associated with the particles moving with a velocity, so that energy what we called Einstein energy. So mathematically it is found that is the relation between the energy and the mass of the particle. That is, we write E is equal to mc². So this energy what we call the Einstein energy. So m is the mass of the particle and c is the velocity of the light. So what is the velocity of light? We know that is the 3 into 10 to the power 8 meter per second. Okay, so this energy what we call the Einstein energy. So another form of the energy is that is the Planck energy. So the energy associated with the particles moving in the direction of the propagation, that energy, that particles we call the wave particle. Wave particles. Okay, now here the energy associated with the wave particles, that energy what we call the Planck energy. Now this is the Planck energy. Okay, this is the Einstein energy, this is the what we call the Planck energy here. So in the Planck energy, that is the energy related to the frequency of the light. That is, I write here, this is the frequency. So particles moving in the direction of propagation, that is what we call the wave nature. This is the part where the particles moving, so in the direction of propagation, what we call the wave here. So how many number of the wave in 1 second, I mean how many number of the waves we travel in 1 second, that is what we call a frequency. So frequency is the number of the waves travel in 1 second, that is what we call the wave frequency here. So we have a two consecutive wave. So how long this two consecutive wave, that is what we call wavelength. Wavelength is the distance between the two consecutive waves. So that is what we call the wavelength. So lambda is the wavelength. Now here, what is the relation between the frequency and the wavelength? So frequency is equal to c by lambda. Mathematically we can have the relation here. Okay, so c is the, we already know that is the velocity of light. So here this is the frequency and this is the wavelength. Now this, when the wavelength is very short, I mean shorter the wavelength, the frequency will be the greater the number of frequency, okay. Now here, then when the wavelength is longer is the wavelength, That means the lesser number of frequency. So we understand from the relation here. So after we know the relation between the wavelength and frequency, the Planck energy we can write as Planck energy is equal to H nu was given here. Then now here I just put it here, H upon C by lambda. So here, so this is what we call the Planck energy related to the frequency or the wavelength of our particles moving in the direction of the propagation. Now here another one is the Einstein energy. This one is the Planck energy. This is the Planck energy. Now what's the difference between the Einstein energy and the Planck energy? Here in the Einstein energy is only the relation between the energy and mass of the particles moving with the velocity of the light. That means velocity of the particles move. Then in our Planck energy, what is that? That is the energy related to the frequency or the wavelength of the particles moving in the direction of the propagation here. So in that case, how these two energies can be related? Now when we related these two energies, we found another relation. What is the another relation we found? The combination of this Einstein energy and Planck energy, the combination of these two energies, we found another relation. That relation is very important. Relation between the what? We found that the relation between the wavelength and the mass of the particle, right? So the relation between the wavelength and the mass of the particle, so that is the one of the very important characters. What should we understand? That is the dual character, can say the nature of a matter. So this dual character of a matter is explained by the one of the very famous scientists. His name is de-Broglie. He could explain the dual nature of our matter. That means the particles behave as a matter or material, and the particle also behave as the wave in nature. So that type of the characters we can discuss in our de-Broglie theory of the dual character of a matter. So in that character, so what he found, that is what we call a de-Broglie equation. Now here, very interesting here, the combination of these two energy, that means Einstein energy and Planck energy. I just write Einstein energy is equal to mc². So that energy, when we combine with the energy of the Planck energy, so or it can be like this one. So these two energy, when we combine, when we related, so we found the relation between our de-Broglie equation. So what is the de-Broglie equation? De-Broglie equation is the relation between the wavelength and the mass of the particle. That is lambda is equal to h upon k, and v is the velocity. How we could related to this, how we could find this de-Broglie equation from our Einstein energy and Planck energy? See, I show you here. See, so here is the E is equal to mc². Here also E is equal to hc lambda. That means one of this I just combine. I compare these two. So I write here mc² is equal to hc lambda here. So now here one of the velocity, of the light can be cancelled. So we found here mc is equal to h upon lambda. Now here this lambda I just going to find out here. That means h upon h divided by okay, mv. This is the no, sorry, this is the c. Now here in this equation we found that c is the velocity of light, but when we consider about the particles, okay, particles like the microscopic particles, so this velocity of light so is equal to the velocity of a particle, right? So now this c I replace by the v, that is v, not again mu. So here I just write our equation H upon mv. So this is our equations found in de-Broglie equation. That means what I conclude that the combination of our Einstein energy and the Planck energy, it found the relation between the wavelength and the mass of the particle. That is what we call de-Broglie equation. Therefore, these three key the concepts of energies and the wavelength, it's very important to understand that, okay, how this de-Broglie equations we found from the two different form of the energy, that is the Einstein energy and the Planck energy here. Okay, now so from the de-Broglie equation here, de-Broglie equation, I just rewrite again. Okay, so this de-Broglie equation, okay, that is the relation between the wavelength and the mass of the particle. Here H is the Planck constant. What is the Planck constant? Value you know, that is the 6.626 into 10 to the power minus 34 joule second. So when we do calculate K in kg, so how we write it, that is 6.626 into 10 to the power minus 34 kg meter square per second. So when we calculate it in terms of the kg, so we just write this one. When we calculate in terms of the joule, we just write this one. So when we can use this joule, so that means here, so this wavelength and mass of the particle, as we know, that is are related to the energy. So when we are talking about the energy, you know that energy we can convert it from the one form of the energy into the another form of the energy. That energy, one of the very important energy, is the kinetic energy. So I write here kinetic energy. How this kinetic energy is related to our mass of the particle, and how this kinetic energy is related to the wavelength of our particles moving. So as we know, the kinetic energy is equal to half mv². So here the kinetic energy is also related to the mass of the particles and the velocity of the particles moving. But the mass of the particle is very important, because when the mass is bigger the mass, that means kinetic energy will be also the very higher kinetic energy. That means when the mass change, kinetic energy also be changed. When the mass is small, kinetic energy will be also small. When the mass is big, the kinetic energy also be very high. So that means kinetic energy is directly proportional, directly related to the mass of the particles when the particles move in a velocity, right? Now, different mass of the particles moving in a same velocity, the kinetic energy also be different, because mass different, kinetic energy will be different. But as we know, the particles moving in the direction of the propagation, that is form of the wave. So when the particles moving in the form of the wave, there will be the frequency and there will be the wavelength. So that kinetic energy, how that kinetic energy could be related with our wavelength. So let me show you here. See, now this mv is common here, right? So this mv, let me multiply here. So now I multiply by this kinetic energy, I multiply by m here. Here also I multiply by the m. Now I just write m square b square. No? So I just cross multiply here. That is m square v square is equal to 2 m e k. That is the our kinetic energy. Now I just find out the mv is equal to root over 2 now m e k. So here it can be also write 2m k, then e k whole bracket, then power of the half. So we can write in the form of this. So here this mv we can substitute here, that is lambda is equal to height upon, now I can write here the root over, that is a 2m okay ek. So here is the relation between the kinetic energy and the wavelength of the particles moving. So from the concept which I just show you, that means when we just analyze, when we discuss of the relation between the Einstein energy and the Planck energy, and how the Planck energy and Einstein energy can convert it into the relation between the wavelength and the mass of the particle, and how the wavelength can be related to the kinetic energy. These are the very important concepts we could understand that, right? So don't forget, So from that concepts we can find out different types of our electromagnetic radiation. So some common electromagnetic radiations I just mentioned here: gamma ray. So I write in X-ray. Then you can say UV. Here is the visible light, then IR. These are the common electromagnetic radiations. So as I said before, electromagnetic radiations are a form of the energies. So what are the types of the energy? I already mentioned, I already explained to you. There are two different types of the energy we can consider. One is the Einstein energy, another is the Planck energy. Einstein energy is the energy related to the mass of the particles moving with a velocity, and Planck energy is the energy related to the particles moving in the direction of the propagation, that is the frequency or wavelength. From the combination of these two energy, we found another relation between the mass of the particle and the wavelength or frequency, we can say, right? Then now from the wavelength we found it, right? So that can also be related to the kinetic energy. Now these are the common electromagnetic radiation: gamma ray, X-ray, UV, visible IR. So these radiations having the different frequency, different wavelength. So now among these, which one is the highest frequency? I just mentioned this. This is the highest frequency, then the X-ray, then the UV. So I rewrite again. So frequency of the gamma ray is the higher than the frequency of the X-ray, and is also higher than the frequency of the UV, and is also higher than the frequency of the visible. Here in our visible light there are 7 colors. So that is what we call the big Q. So these 7 colors are there in our light. Then the frequency is higher than our frequency of the IR. In our IR also we have 3 IR zone. One is the near IR, then and simple IR, then another is the far IR. That means near IR is nearer to our red color of the light, and far IR is the far distance from our frequency of the red light. So that we consider as the far IR, near IR, and the middle one we can say the IR also. So these are the our different frequencies of the different electromagnetic radiation. As we know, frequency is the c by lambda means more frequency, short wavelength. Less frequency means the longer wavelength, right? So here, as we know, gamma ray is the highest frequency. That means the wavelength will be the opposite. The reverse of this. The frequency of the radiation. Here we can say that this is the longest wavelength. That will be the higher will be the longest wavelength than the length of the visible light, and then wavelength of the UV, and then wavelength of the X-ray, and the very shortest one is the wavelength of the gamma ray. So these are the different wavelength of the electromagnetic radiations known. So this idea you please keep remember, and what are the relation between the different parameter, that energy, mass, energy, wavelength, and energy, and wavelength and mass. So that relation, so you please understand and please learn it. And when we have these things, we can find the different answer when any types of the question come up in your any competitive examination, right? So keep it remember and just try to remember it.